Hello, everyone. Yeah, welcome to this tutorial on profit inequalities and their implications to pricing mechanisms in online algorithms. So this tutorial is going to be in three parts, where in the first part, I'm going to give you a broad overview on what are profit inequalities, like what are some simple profit inequalities, and broadly discussing like their implications to mechanism design in online algorithms. So I will cover some proofs, but the focus will be more on like the general overview or on the connections. And in parts 2 and parts 3, part 2 will be by Mihal and part 3 by Thomas, they'll be going more into the details of the proofs and some of the results that I'll mention. So yeah, feel free to ask questions on the chat. So we'll be doing questions over chat, and Thomas will basically let me know whenever there are some questions, and he'll stop me in between. But so let's get started with the profit inequalities. So what's the basic profit inequality? The setup is as follows. There are n distributions. So think of these as n boxes, each of the boxes containing some reward, where the reward in the ith box is drawn from some distribution di. These are all independent distributions, and these distributions are known to you upfront. So these are just like d1, d2, d3, d4, like some n distributions. And the problem is as follows. You're going to get outcomes from these distributions one by one. And in step I, or like ith time step, you're going to see the realization or like an outcome of xi, which is a random variable drawn from distribution di. Your goal is to immediately decide, are you taking this reward or not? Are you immediately accepting or rejecting it? You're only allowed to accept at most one of these boxes. So your goal is to maximize the reward of the box that you select or accept. So to say a little bit more, so your goal is that wherever you stop, I mean, you can also view it as a stopping time problem, because the box that you accept, you can think of that as the location where you stop. Your goal is to maximize the reward of that accepted box. And the question is, how well can you do as compared to the expected max of all these random variables? So if you compare yourself to a prophet who knows maybe the outcomes of all these random variables, the expected value of such a prophet would be just the max of all these boxes. How well can your algorithm do as compared to this benchmark, the expected max of all of them? So here's like a small animation. Like suppose x1 takes a value of 4. The question is, do I stop or do I continue? I know the distributions d2, d3, d4. Maybe d2 is like say uniform between 0 and 5. d3 is some other distribution. d4 is some other distribution. But I need to make a decision about x1 immediately before I go to d2, like the outcome. Suppose I decide to reject it, then I go to see the value of x2. And maybe x2 turns out to be 6, and I accept it. So my value is 6. And in some sense, the game has ended. You end up with a reward of 6. Had you continued, maybe x3 turns out to be 2 and x4 turns out to be 10. But OK, you cannot now change your decision. You've already taken x2, and that has reward 6. So the question is, like, whatever is your stopping rule, like, or whatever is your algorithm, the box that you accept, what's the expected value of that as compared to the expected max of all of them? And the classical profit inequality basically says that there exists an algorithm which on average gets you at least half of this expected max. So this was already shown in the late 70s by Krangle, Suxton, and Garnick. So this is going to be the main basic profit inequality, which is a classic result more than 40 years old. So that there exists an algorithm that gets you this. And I'll be more soon telling you about the proof and many other things. But as I'm saying, like it has many, many applications in many fields, such as online algorithms and pricing mechanisms, which I'll be going more in the detail. So here's the high-level overview of the tutorial. So in this first part of the tutorial, I'll basically be discussing this. First, I'll cover the proof for the single item profit inequality. And then I'll broadly discuss how like this profit inequality and its generalizations have implications to pricing mechanisms in online algorithms. Part 2 will be by Mihal, where she'll be focusing more on matchings, like how do we design profit inequalities for matchings. And in particular, she'll be focusing on techniques such as online contention resolution schemes. Part 3 will be by Thomas, and Thomas will be talking about much more bigger generalizations beyond matchings to combinatorial auctions and even like to matroids and other combinatorial settings. And he'll be talking about a technique known as balance prices. So part 1 will more be like this part will be more on the broader picture. And I'll be giving some proofs, but like the focus will still be on the general theme. Okay, so let's get started. So as I was saying, the profit inequality, the classical profit inequality is you can get a half of the expected max. And also this half is actually tight in the sense that there are examples where like you cannot hope to improve this factor half by by a constant. So here's like a very simple example. Imagine you just have two boxes. X1 takes deterministically a value of 1, and x2, on the other hand, takes a very large value, like a 1 over epsilon. Imagine epsilon like very close to 0. So x2 takes a very large value, 1 over epsilon, with a small probability epsilon, and it's otherwise 0. Now, you have only two boxes. First, my claim is that any online algorithm has value at most 1 on this instance. This is simply because either your algorithm takes x1 and it gets a reward of 1. If your algorithm decides to reject the first box, then it goes for x2. But again, the expected value of x2 is just 1. And notice if x2 turns out to be 0, your algorithm is no longer allowed to go back to x1 and take it. So any online algorithm can take at most 1 value, whereas the expected max of these two random variables is pretty much 2, like a simple calculation for epsilon tending to 0. And this already shows that the ratio between any online algorithm and the expected max can be like 2. And what I'll show you soon is like also that there are algorithms, simple algorithms that can now also guarantee you that you get at least half of expected max. In fact, like these are not very complicated algorithms. These are very simple algorithms, which I call the threshold algorithms. So what's a threshold algorithm? So I'm calling it alg tau. It basically just sets a threshold or a price of tau. So tau is some number which I'll tell you how to compute. But once you have chosen this threshold, your algorithm is very simple. Just select the first box, which takes a value more than tau. So select first xi, which is at least tau. And that's the algorithm. And I'm going to soon tell you that there are some thresholds that you can choose, which already guarantee you half of the expected max. So to give you some examples of such thresholds, one is this threshold, which I'll call the mean threshold, where the threshold is chosen to be just look at the expected max of all these xi's. Notice you know all the distribution, so you can compute this expected max xi upfront and set the threshold to be half of that. So this is what I'm going to call, say, the mean threshold. Another popular threshold is the median threshold. So the median threshold is chosen as follows. Like it's set such that the probability that all the random, like that there is a random variable which is above this threshold is a half. So think of like the max of x1 to xn, like all these random variables. The probability that your max exceeds this threshold is a half. So assuming like your distributions are continuous, there are no like say point masses, which you can always ensure by like slight perturbations. There always exists such a threshold such that the max exceeds this, exactly probability half. So this is what I'm going to call the median threshold. And what's the result? Like what's known is that both these median and mean threshold algorithms, they get you a value which is on average at least half of expected max. And for the median threshold, this was shown by Esther Samuel Kahan in 1984. And for mean, this was studied by Kleinberg and Weinberg. And the proof is also like very simple. It will fit in this entire slide. It's just like 3-4 inequalities. So it's not very important in the sense for the rest of the talk, but I want to give you a flavor of how these simple proofs work. At least this proof works. And in fact, this proof will be repeated probably like in variants in other talks as well by Thomas and Mihal. So, but let's have a look at like how we prove this result. So I'm going to prove it for the median threshold. So not for the mean, but pretty much the same proof works. And recall like what I've defined, p tau is nothing but the probability that there is at least some variable that exceeds tau, that is at least tau. And for this threshold algorithm, this is also exactly the probability that your algorithm selects something. I mean, if all the variables are less than tau, then you don't select anything. If at least one of them is exceeds tau, then you get something. I'll also use one inequality, which is written here. It's basically just saying it's a very simple inequality. It's saying that max of x1 to xn, like for any n random variables, is at most tau plus some additional value. So this will be, and in fact, I'm going to upper bound this additional value by the summation of xi minus tau. So I mean, sometimes we'll use this, and x plus is just the notation max of x comma 0. So let's see like how the proof goes. The first inequality says that the expected value of your algorithm, you can think of this as some probability with which you get the base contribution, like the threshold value, which is exactly p tau times the tau. So p tau is, notice the probability that your algorithm selects something. So whatever your algorithm selects, think of dividing that value into two portions. One is the value which is below tau, and one is the value above tau. So the value below tau, you get it exactly with probability like p tau, which is the probability that you select something, plus you get some excess value. Now let's look at this second part. What is this excess value that you're getting? So the excess value that you're getting from the ith variable is nothing but xi minus tau, the non-negative part, like the max of this comma 0. But this contribution is made only if all the random variables before I, like all the XJs which were before I, they turned out to be less than tau. So only when all the random variables before I, they are less, then your algorithm does not accept any of them, and then it reaches I. And if it reaches I, then okay, if xi is larger than tau, then your algorithm gets this excess value. If xi is smaller than tau, then anyways, this is 0, so it doesn't matter. So you can basically just think of your algorithm's value as this some base contribution plus this excess value. And once you have this expression, now it's kind of again very simple. Just by the definition of p tau, this probability that all these random variables are less than tau, you can lower bound this by 1 minus p tau. Because notice p tau, like 1 minus p tau, is the event where all the random variables are less than tau. So that includes even like these random variables which are before j. So that's you have like a simple inequality, and you have this summation. And now this summation I can simplify using this inequality, like the inequality which is there in the box. You just move this, like you get like max xi minus tau. This is what you have, and take expectation. And once you have this, then the proof is basically finished. I just substitute p tau. So for median threshold, p tau is exactly half. Remember, like the way I defined p tau, like the median threshold is tau such that p tau equals half. So I'll just put half here, p tau equals half, and like just this tau terms cancels out, and you get half of the expected max. For the same proof basically goes for the mean threshold as well. You'll just substitute in the last step. Tau will be replaced with the expected max over 2, and again you'll see like 2 terms cancel out, and whatever you're left with is exactly half of expected max. So yeah, hopefully you followed it, but even if you got lost, all I want to say is like it's a very simple proof. You just go over these inequalities, and it won't be required for the rest of the talk, but I wanted to give you an idea, like basically this idea of setting a threshold and analyzing the value of your algorithm as some contribution up to this threshold plus some excess value. And this idea is going to appear later on as well. And like this idea of setting a threshold or a price, some people also like to call it price, that will play a crucial role in designing these pricing mechanisms. Good. So let's continue. So here's the outline for the talk. I just told you about what are these single item profit inequalities. Now the next part of the talk will be more about like what are their implications of this profit inequality and its generalizations to pricing mechanisms. In particular, like it will help us design simpler mechanisms for both like welfare maximization and revenue maximization. What the word simpler means, I'll tell you like as we come to it. There are multiple interpretations of what's simpler. And then the next part of the tutorial will be on like the implications to online algorithms. And here the biggest benefit of studying these profit inequalities is it helps us do some kind of beyond the worst case analysis. So there are like these online problems where in the worst case, you cannot hope to do much. But once you view them as a profit inequality problem, then you can do much, much better. And finally, I'll conclude with some of the other directions. Okay, so let's start off with applications to mechanism design. And in fact, let's start off with the simplest problem, the single item auction design. So here you have n bidders, and each of the bidders has some valuation for a single item. So maybe there are like all these animals, and the item that you have is a patch of grass, and you want to allocate to one of the bidders. Maybe the cow wants it the most or something. So it's an auction design problem in the sense that you need to come up with a mechanism or an auction which decides who gets this patch of grass. The values of all these bidders for this patch of grass, so the value of the ith bidder is denoted by vi, which is a random variable drawn from some known distribution di. So that's what I'm going to assume. Your algorithm or your mechanism knows the distribution di, but the exact outcome vi is not known to you. So it's a private value in the sense your algorithm doesn't know. So what's your algorithm allowed to do, or your mechanism allowed to do? So this is the classical setup of mechanism design. All these bidders, your mechanism is allowed to ask all these bidders to report their valuations. And I'm going to write this as vi tilde. So I'm putting a tilde there because they may or may not report their true valuation vi. They could be lying about their valuation. So that's why I'm saying like a vi tilde. After taking all these valuations as input, your mechanism or your algorithm decides who gets this patch of grass and how much payment that person makes, that bidder makes. All these bidders are strategic in the sense that they are trying to maximize their utility, which is their valuation minus the payment. So all these bidders, that's why they are going to, all these bidders, they know the mechanism that you're running, the algorithm that you're running. based on the knowledge of this algorithm, they're trying to come up with a bid vi tilde, which need not be vi, so as to maximize their expected utility or their utility. And what's your goal? Your goal is to come up with a truthful mechanism. So what do I mean by truthful mechanism? It's basically saying that you want to guarantee that vi tilde is basically equal vi. Like all these bidders, they have no incentive to misreport. So while maximizing, so you want to design a truthful mechanism that maybe maximizes the welfare or the revenue. So welfare is like whosoever gets the item, their value is maximized, like that person is the highest bidder. And the other question is about revenue maximization, maybe how much money you're earning from this auction that you want to maximize. In case this is getting too abstract, like here are like some simple examples. You might have heard of like first price auction and the second price auction. In the first price auction, you give the item, like ask all these bidders their valuations, and then give the item to the highest bidder and charge them their bid. So this is not a truthful mechanism, simply because like maybe the highest bidder wants to underreport. Because if they report truthfully, then you're going to charge them their entire valuation. They'll be left with effective utility of 0. On the other hand, second price auction is you give it again to the highest bidder, but charge them the second highest price. And by simple case analysis, you can show that this is actually truthful. So again, this is like a very classical model of auction design. So you have these bidders drawing some valuations from some distribution. You know the distribution, you don't know the outcomes, and your goal is to come up with a mechanism so as to maximize welfare or the revenue. So, okay, so this was just like the setting up, and now I'll tell you like how we go about, like how we can use profit inequalities. Let's first look at welfare maximization for the single item setting. So one could run second price auction here. And second price auction is amazing because it's truthful and it maximizes the welfare, because it actually gives the item to the bidder who reports the highest valuation, like who makes the highest bid. And because bidders are truthful, this is also their highest valuation. So it maximizes welfare. But there are like a bunch of challenges of second price auction. For instance, like the bidder payments are relatively natural. I mean, the highest bidder has to pay the second highest bid. So they sometimes have to like trust the platform, that the platform is not cheating against them. There are also other issues like, okay, maybe the bidders need to report their exact values. And I mean, there are like a bunch of challenges with running second price auctions. For instance, there's like a beautiful survey by Ospol and Mildrum, like who talk about exactly like the challenges of these second price auctions and their generalizations, like Vickrey auctions. On the other hand, like, so now this is where I want to say, like, I want to use these profit inequalities to design simpler algorithms or simpler mechanisms. What do I mean by simpler? So let me give you an example of an auction, the so-called fixed price auction. So what's a fixed price auction? In this auction, you're going to set a fixed price for your item. So this patch of grass that you were trying to sell, I'm going to set some fixed price for this based on the distributions. And then the bidders come in an arbitrary order, and offer them, okay, if you want the item, you have to pay me this much price, and you can take it. Like, so whosoever is the first bidder that walks into your shop and is willing to pay the price, they gets the item, and that's it. So you're basically going to sell the item to the first bidder, whosoever is willing to price. And this is much simpler. I mean, for instance, the payment is already pre-decided. So that's simpler. I mean, all these bidders also don't have to know their exact valuation. All they need to know is like whether they value the item above or below this price. So there are like a bunch of advantages of fixed price auctions. And now you might already be seeing like the connections to profit inequalities, because this is precisely what profit inequalities, our algorithm, was giving us. The profit inequality basically said exactly this, that if you set this price to be maybe the mean, like the half of the expected max, or say the median threshold, both of them actually give you that on average, the expected welfare of your algorithm is going to be half of the expected max. So this observation was first made like in a paper of Mohammad Haji Agahi, Bobby Kleinberg, and Thomas Sandholm. But what I'm trying to say here is that this is like a very simple auction. And this is like a very simple setting, like just a single item auction where already like second price auction already does optimally, like in many senses, it maximizes the welfare and it's very simple. However, like we can even simplify it by running these simpler, like these fixed price auctions, which already like they're much simpler and they already give you like immediate, like profit inequalities already imply some non-trivial, have like non-trivial implications for this single item welfare maximization. So that's like the first like high level result. And I'll soon tell you, like once we move to like more than a single item, then these implications become even more less and less non-trivial. They become like more and more non-trivial, and we don't even often know like how to get them using alternate techniques. So I do want to tell, like, okay, there's some caveats to this. This is not like perfect in the sense, first of all, okay, although it's truthful and it is much simpler, notice I'm no longer getting a perfect welfare maximizing. I'm getting an approximation. I'm getting like half of the maximum welfare. Also, I've made a stochastic assumption. For instance, for VCG mechanism, actually, you don't even need to make the assumption that you know the distributions of these bidders. So fixed price auctions, like they give you a lot of advantage, but I mean, okay, there are some drawbacks as well, which I do want to point out to you of running this live auction. Okay, so now let me take a step towards revenue maximization. Again, the single item setting, single item revenue maximization. You want to, again, sell this patch of grass so as to maximize your revenue. So what's known about revenue maximization? So here again, okay, what's the model, as I was saying, is like these bidders are drawing their valuations from some known distributions. Actually, we know what are the optimal mechanisms for this setting as well. So in a classical result of Meyerson, what he basically showed was that you can run some kind of a second price auction, not on the original valuations, but on the virtual valuations. So this is like some transformation. So you don't need to, I mean, if you've not seen this before, you don't need to really digest the expression. But all it's saying is, the main takeaway is that there is a transformation from your original valuation to some virtual valuation space. And basically in this virtual valuation space, you run the second price auction, and turns out that is actually maximizing your revenue. It's both truthful as well as it maximizes revenue. So this is the classical result of Meyerson. And I mean, yeah, Meyerson is a Nobel laureate and like one of the founders of mechanism design. And he also showed, like, I mean, this expected revenue is nothing but the expected max of these virtual valuations. And this is where you might already be seeing some connections to profit inequalities, because in profit inequalities also, we were getting expressions of this form, like our benchmark is precisely expected max of the random variables. I mean, usually we don't have this transformation VI hat, but that's precisely the connection to profit inequalities. So up to this tilde, like if you really ignore it, like it's basically saying it's the expected max of these some random variables. And so although Meyerson's mechanism is beautiful, both theoretically and like it gets you the optimal revenue, there are some disadvantages. Like for instance, the highest bidder may no longer win the item. So notice the highest bidder in the original space, once you transform these valuations, it's no longer guaranteed that after the transformation, this highest bidder will also have the highest virtual value. Hence, the highest bidder may no longer be the one who gets the item, which is not a desirable property if you're trying to run this auction in practice. Another disadvantage of running Meyerson's auctions is that, okay, the payments are pretty complicated. You're running this second price kind of an auction in the virtual space, which gives you some like complicated payment functions, again, which are hard to justify if you're trying to run such an auction in practice. And these are things like which have been discussed in more detail in many works, in particular in this paper of Jason Hartline and Tim Roughgarden on simple versus optimal mechanisms. Now, so where am I heading to? I'm basically heading to this theorem that you can actually use profit inequalities to design much simpler mechanisms for, again, the single item revenue maximization. In particular, you get a much simpler mechanism. So I'll tell you soon like what this mechanism is well, although I won't go over the proof, but it's simpler in the sense that it will get rid of all these disadvantages that we discussed. And it gets you a half approximation to the optimal revenue. So that's the beautiful thing about this, is it's getting you like a much more simpler mechanism, which is again like which is comparable to the optimal mechanism. So I won't be discussing the proof primarily because I mean that will, like, if I have to go over the proof, I'll have to introduce so much about revenue maximization, which will take a lot of time. But I'll encourage you to have a look at Tim Roughgarden's book on 20 lectures in algorithmic game theory, where he goes over this proof in detail. But let me still tell you, like, what is this simplified auction using profit inequalities? It basically says that you're going to run second price auction with some personalized reserves on the original valuations. So what do I mean by that? Basically, the auction is of the following form. Look at the distribution of each bidder. Based on their distribution, set a reserve price for each bidder. So set a bidder-specific reserve price, which is a function of their distribution. And now you just sell the item to the highest bidder who exceeds their reserve price. So all it's saying is, like, if you are going to pay, like if you're offering me something which is less than your reserve, then I'm going to totally ignore you. But as long as you offer me something, you make a bid which is more than the reserve, then I'm basically going to run like a second price auction. And that already gives you like a half approximation to the optimal mechanism. And this is great because for instance, like the highest bidder is now going to win as long as they cross their reserve price. And also their payments are also much simpler. Good. So this was all what I want to talk about single item auctions. And now let me take a step towards multiple item settings. So again, like what we want to study is like what happens for this multiple items. Like we have a bunch of bidders, n bidders, m items. And this time each bidder has some function. I mean, they can get a subset of items and their valuation is a private value, which is drawn from some known distribution. So the distribution is known, but this valuation VI is not known. And notice this valuation is now a function. It's a set function. For every subset of items, what's their value that they're getting? Like what's the non-negative real value that they're getting? Again, the goal is going to be similar. I mean, you want to design a mechanism which is going to take as inputs some reported valuations of these bidders, VI tildes. You want to come up with some allocations in payments. All these bidders are strategic. They want to maximize their utility, which is their valuation minus the payment. And again, you want to come up with a truthful mechanism, which maybe either maximizes the welfare, sum of the valuations of all these bidders, or the payments, which is the sum of the payments or the expected payments. So the question is, again, like what can we do about this? And here you'll see like actually profit inequalities actually give you much more, they'll give you like much more beautiful results in the sense these are things that we don't even know how to obtain using other techniques. So first of all, okay, what's about multiple items welfare maximization? Again, there are auctions like such as the VCG mechanism, which is, if you haven't heard of it, it's like generalization of the second price auction, which is both truthful and it maximizes the welfare. So it's like, it gives you the maximum possible welfare. So it's optimal in that sense, and it's also truthful. However, the problem with the VCG mechanism, it's not polynomial time. Its running time is no longer polynomial time beyond simple valuations. So notice this valuation function were some set functions. If you go beyond some simple valuations, then it's no longer polynomial time. So what do I mean by simple valuations? So here's like one hierarchy to keep in mind. Like additive functions are the simplest ones. Their valuation of two, like A union B, is nothing but the valuation for set A plus valuation for set B. And I mean, more general valuations you might have heard of are like submodular, XOS, or even subadditive. I mean, I've written the definition of subadditive valuations, but again, you don't need to understand exactly what these valuations are. But these are much more natural, like these are bigger classes of valuations, which again appear a lot in practice. So subadditive valuations are also known as like complement-free valuations and all. So the point is that as soon as you move beyond additive valuation, so for additive valuations, you can actually run the VCG mechanism and it runs in polynomial times and it's truthful and maximizes welfare. So it's amazing. But as soon as you move to like submodular valuations, XOS or subadditive, these problems are actually known to be like NP hard or even worse. And hence you cannot actually basically run the VCG mechanism, and VCG mechanism doesn't give you anything. Instead, a much simpler auction, I mean, a dream auction would be some kind of, again, a fixed price auction. So what's a fixed price auction in this combinatorial setting? So what a fixed price auction here basically means is I'm going to set fixed prices for all the items. So you have like all these M items. For each of these items, I'm going to set a price. Now these bidders are going to again come to your shop one by one. Among all the remaining items, they are allowed to purchase as many as they like by paying the sum of the prices of the items. This is like a very natural auction, the one like that happens a lot in practice at a grocery store. Like these bidders come in an arbitrary order. Among the remaining items, they basically just select the best set that maximize their valuation minus the sum of the payments of these items. So this is a fixed price auction, a very simple auction, which is both, first of all, polynomial time and it's truthful. It's a polynomial time because it's like just a single query that you need to run in this Oracle model. And now the amazing result is that actually for welfare maximization, you can actually run fixed price auctions that already get you very good approximations to the optimal welfare, to the maximum possible welfare. In particular, for submodular or XOS valuations, you again get the same two approximations. So remember, like for single item, we were getting this half of expected max. Basically, what the claim here is, this theorem is saying, is actually that same factor half, you can get it even up to like submodular or even XOS valuation. So you can think of this theorem as some kind of like the classical profit inequality on steroids. Like it's a much powerful setting, even for like submodular or XOS valuations. There exists some fixed prices you can set up on these items such that these bidders come one by one, take their favorite set of items and make these payments, like a very simple practical auction, fixed price auction, and that already gets you a 2 approximation or a half approximation. to the maximum welfare. For submodular XOS, for subadditive, the best current guarantees that we have is the log-log M approximation. And this is like, again, very, very powerful because notice, like, for instance, for submodular XOS, we don't know any other alternate ways of getting a constant approximation. And so that's very powerful. So I won't be discussing the proof right now. Like Thomas will go a lot more in detail in the part 3 of the tutorial. But I wanted to give you a highlight, like one of these major results of profit inequalities and its implication to auction design for this welfare maximization. So yeah, and Thomas will discuss this like in great detail, this result. Good. So now let's also have a look at like multiple items, revenue maximization. So again, like what I want to clarify here, like what does the word simple here meant in this case? Simple here meant, first of all, this fixed price auctions are much simpler in any sense of simplicity you might think of. Also, simplicity here meant polynomial time. So your algorithms are like now polynomial time, and they are like very simple to implement. So now what can I say about multiple items revenue maximization? Again, you have these n bidders, m items. Turns out Meyerson's mechanism, I mean, cannot be extended beyond the single item setting. So for these like n bidders, m items, you cannot really run Meyerson's mechanism. So there's no natural way of designing a mechanism which gets you something like the optimal like revenue maximizing auction. And now this problem has been again greatly studied. As you can imagine, it's a very fundamental problem in the field, like multiple bidders, multiple items. You want to just maximize the revenue. And there are like more and more general settings you can consider. Like the simpler setting might be like single bidder, multiple items, multiple bidders, multiple items, multiple combinatorial bidders, like some modular subadditive bidders with multiple items. All these problems have been studied. I won't be going again over the proof of any of these things, but the main takeaway message is using these profit inequalities, you can again get very good approximations for all these revenue maximization problems. So in particular for submodular and XOS valuations, you can again get constant approximations. And for subadditive valuations, you can again get a log-log M approximation. So like these results use many other tools besides profit inequalities, but profit inequalities still play a major role in them. For instance, like to give you a small example, like for subadditive valuations, up till recently, the best known approximation was a log M approximation. But last year, first, like researchers made progress on a profit inequality for subadditive profit inequality. And then they also used that result to improve the revenue maximization and get like a log-log M here as well, which was the result of Paul Ditting, Thomas Kesselheim, and Brendan Lucier. But I guess all I want to say is like the main takeaway messages here, simplicity meant like in polynomial time. And in polynomial time, we are getting like very good approximation to revenue maximization using some generalizations of profit, the classical profit inequality. And that's where profit inequalities play a major role. So this is something, again, like because it's a long, very active area of research. So we won't be discussing it in the tutorial, but I'll encourage you to have a look at these papers. Good. So let me wrap up this part of the tutorial, like on mechanism design. So what's the main takeaway message? What the main message is that, okay, we can use profit inequalities to get much simpler fixed price auctions, which are also like in polynomial time. And they work both for welfare as well as revenue maximization. They work for combinatorial auctions and even like more general combinatorial feasibility constraints. You can put some matroid constraints and things like that, which will be again discussed in the later parts of the tutorial. I do want to tell, like, okay, it's again, like it does not solve everything. There are some drawbacks as well. For instance, for welfare maximization single item, we did make a stochastic assumption, whereas VCG mechanism does not require any stochastic assumption. For revenue maximization, turns out you actually have to make a stochastic assumption, otherwise there's nothing that you can do. Also, we are getting approximation algorithms, again, which are kind of necessary if you go to combinatorial auctions or any of these NP-hard problems. But for a single item setting, we know optimal mechanisms, which are not at all approximate. They give you like one approximation. So, but yeah, I mean, I wanted to give you a high-level idea of what are the benefits and the drawbacks of designing mechanisms using profit inequality. Good. So now let me briefly discuss like some of the implications to online algorithms, and then I'll conclude. So what's an online algorithm setup? Here, inputs arrive one by one, and your algorithm has to make immediate and irrevocable decisions. Okay, so what's the simplest setting? Like you have a sequence of bidders coming in or like sequence of numbers coming in. You want to select the max number. So that's like a very simple problem, a simple online problem. You have n numbers coming, V1 to Vn. You want to select the max of them, the largest item or the largest bidder. Turns out in the worst case arrival, when you have no knowledge about these numbers, there's not much you can do. I mean, the reason being, there could be the input could be of this following form, like maybe the first number is like $1, the second one is $1 million, the third one is a million square, million cube, and so on. So they are increasing very, very fast. You have no idea whether I accept the next number or do I reject it. Maybe the next one is going to be 1,000,000 times more. And then at some point, all the future numbers are going to be just zeros. So for such a simple instance, like simple looking instance, actually in the worst case scenario, there's nothing you can do. I mean, because you have no idea what's the scale of the problem. Are you fighting for pennies or are you fighting for billions of dollars? I mean, and that's actually an issue. Like it's a very simple looking online problem. Like you want to get the max, and already there's nothing you can do in the worst case model. And as you might have already noticed, like this is precisely what profit inequality solves. In profit inequality, you make an assumption that these numbers are not adversarially chosen, but these VIs are drawn from some known distributions DI. And here, profit inequality tells you exactly that you can get a half of the expected max. So the way to interpret this profit model is, although you're making more assumptions, it's helping you go beyond the worst case. Like in the worst case model, you could have at best done is chosen one of these numbers at random, which gives you like an n approximation, but now you're getting like a 2 approximation. And you can also think of it as some kind of a semi-random model, which is more powerful than IIT. And this was just the single item setting, like when you were just selecting a single number in this online sequence. As you can imagine, like you can go much beyond that for online maximization problems. There's the general online packing problem, where again, you get a sequence of numbers coming one by one, VI drawn from known distribution DR, and you have some feasibility constraint. Like in the last case, the feasibility constraint said that you can only choose one of these n numbers, but you could have more general packing, like feasibility constraints. And then the question is, like, you have to immediately decide whether to accept, reject, and maximize the sum of the selected values. The question is, what can you get as compared to the expected max, the expected hindsight optimum? And there are many, many results known here, like for cardinality constraints, matching constraint, matroid constraints, you can again always get constant approximations. These will be again discussed in detail in tutorial parts 2 and 3. Even in fact, for general packing constraints, like an arbitrary packing constraint, a result of Aviad-Rubinstein shows you can get a polylog approximation. You can even study like beyond additive objectives, like to submodular and subadditive objectives. Here again, depending on what constraint you're working with, you can get like similar approximations. But I just want to give you like a high level flavor of like how profit inequalities help. And again, all these problems in the worst case model, you cannot do anything. I mean, because they are generalizations of the single item problem, and already like for the single item problem, you cannot do anything better than an approximation. Let me also tell you, like profit inequalities have implications to minimization problems. For instance, like here for a minimization problem, I want you to think of a problem where requirements arrive one by one, and you have to meet these requirements so as to minimize your total cost. So the requirements have to be met while minimizing cost. To give you a more concrete problem, here's the online Steiner tree problem. So what's the problem? In this online Steiner tree problem, you're given a graph. So imagine you're given this graph, and you're also given a root vertex. So there's a root vertex. You're going to get requirements one by one. Requirement is nothing but a vertex. I tell you like some vertex, and your goal is to immediately connect that vertex to the root by purchasing a subset of the edges. The goal is to satisfy all these requirements, like all these vertices that arrive, to connect them to root immediately while minimizing the sum of the total purchase costs. So like a small animation, maybe this request V1 arrives. As soon as V1 arrives, you have to immediately purchase a subset of edges so as to connect it. Maybe I purchase these bottom edges. So my cost is 2 and opt is also 2. In some sense, like nobody can do anything better than 2. And now maybe another request arrives, this V2 arrives. Okay, and V2 is no longer connected to the root. V2 is not connected, so I have to purchase one more edge. And notice now my algorithm's cost has become 3 because it has purchased 3 edges, but opt is still 2 because opt could have initially chosen the upper path, and that would have just paid a cost of 2. So this is the online Steiner tree problem. Like again, like why is this interesting? Like, I mean, so your question, I mean, broadly is that what value compared to the hindsight optimum can you get? Like how much more do you have to pay the cost? Like what's the factor you want to minimize this? So in the offline problem, already this is NP hard, so you have to get some approximations. You cannot do it optimally, but I mean, minimum spanning tree gives you a 2 approximation. Online, it's known that actually you cannot do for worst case arrivals. The best you can get is like a log-n competitive ratio, like a log-n approximation. So which is decent, but it's not very good. I mean, it's not a constant approximation or something. So for the worst case setup, all I'm saying is you can basically somehow generalize this example and show that log-n is the best you can do. And so the question is, how can we do better? And this brings us to like some kind of a profit model for the online STEINER tree problem. And in general, like for any online problem, where I want to say that the ith request is going to be drawn independently from a known distribution. It's not a worst case arrival. It's like from a known distribution, but the outcome is not known upfront. So this gives you the profit STEINER tree problem, where the same thing, just that the request arrives from a known distribution. And your goal is to again minimize the competitive ratio as compared to the expected hindsight optimum. And so, I mean, you don't have to restrict yourself to just STEINER tree problems. There are many other problems you can study: online facility location, online vertex cover, and all of these. Again, for all of them, there are some super constant guarantees that you can get in the worst case arrivals. A beautiful result of Naveen Garg, Anupam Gupta, Stefano Leonardo, and Piotr Sankowski was that for all of these problems, in the profit model, actually, you can get a constant competitive ratio. So rather than getting this log n competitive ratio, you can do much better. You can get a constant approximation in this profit model. So again, this is helping you go beyond the worst case, get much better guarantees in this profit model. So, and in fact, like the approximation is also like very simple. It's just they get like a 4 competitive ratio for the online STEINER tree problem. The proof is also very simple. Like it can fit in just this slide. Let me at least tell you the algorithm. So the algorithm is as follows. It's a very beautiful algorithm. You just take one sample from all these distributions upfront. So you know the distribution. Take one samples from all of these distributions. And right in the beginning, to prepare for your actual request, just construct a minimum spanning tree on these samples. And now your real algorithm is going to be just like construct first this spanning tree. And then like whenever a new real request comes, just greedily match it to connect it to the minimum spanning tree that you already constructed. So that's the simple algorithm. You just prepare in advance using these samples and then greedily meet the requirements. That the claim is that this algorithm already gets you like a 4 approximation. And notice, like, I mean, this minimum spanning tree that I'm constructing offline, that has at most a constant of 2 times opt, because again, it's being drawn from the same distribution. And so it's like the optimal STEINER tree has the same value as opt, but minimum spanning tree gives you a 2 approximation. So that's the cost. And the proof is also very simple. I mean, it's basically based on one observation, which is subtle. I mean, it requires some care, but it's, I mean, simple in hindsight, which basically says that the greedy cost of meeting the ith request can be charged to or can be upper bounded by the cost of connecting this fake request VI hat that you had in your sample to the other vertices of the minimum spanning tree. So you can, I mean, this inequality needs a little care, like, I mean, you have to think about it a bit carefully to verify that it works out, but it works out. And once you have this inequality, then you just sum it up over all the requests and you get like a simple 4 approximation. So I'll skip over the details. But okay, so the main takeaway again, like what are the profit inequality model is that it helps you go beyond the worst case model for both these maximization and minimization problems, for a bunch of such maximization and minimization problems. And the message for like if you want to come across any online problem, so the main takeaway for you, the technique would be, first of all, think of this profit model because it might help you go beyond the worst case. Moreover, it might be also interesting because it's a new way of thinking about the problem. So if maybe you're stuck on your online problem, you don't know how to make progress, you might want to first make progress on this problem in the profit model, which gives you more room to play, and then maybe try to extend it beyond to the worst case settings. Good. So now I'll very quickly give you like a high level some of the other directions in which profit inequalities have been studied, but this will be like very brief, and I'll conclude in 2 minutes. So one thing you might notice, like the profit problem, again, you have known these distributions, you want to maximize the accepted value. We've been always comparing ourselves to the expected max of all of these random variables. What if I want to compare myself to the optimal policy? Like, why is my benchmark the expected max? Can I do anything compared to the optimal policy? I mean, although the other benchmark, like the expected max is a much stringent benchmark. I mean, but maybe like, because you cannot hope to achieve it, maybe this benchmark is more attainable. And in fact, like for single item setting, there's a very simple dynamic program that you can run. I mean, basically just run a dynamic program right from the end, like the last variable you'll always accept. The second last you'll accept it as long as its value is more than the value of the last variable, like the expected value of the last variable, and so on. You can run a very simple dynamic program that gives you the optimal policy. You can define such an optimal policy even for more general settings, like like if you go to matroids or matchings or any of these things. But none of these algorithms, this policy is well defined, but it's not in polynomial time. So the question becomes, how much can you get as compared to the optimal policy in polynomial time? So there are some results known in this line of work, but there's like many, many open questions. Like even for matroids, you don't know anything how to do better than a half approximation. This is like one direction which is very actively being studied recently. Another direction which is being studied is like, okay, we've been always assuming that the distributions are known and the arrival order is worst case. Like what if the arrival order is not worst case? Maybe like there is some more control to this arrival order. Like two popular models here are the free order and the profit secretary. In the free order, your algorithm chooses the order. So the distributions are fixed. And as soon as maybe your algorithm decides, maybe show me the value of the fifth box. So you get to see X5 and you have to immediately decide, are you taking it or not? So you cannot like postpone your decisions, but you can choose the order in which you are going about them. Another popular model is the profit secretary, where these arrival order is chosen uniformly at random. Again, this has been studied. There are like many, many works. I'm just going to flash them, but I mean, you don't need to, but like this is again, interesting line of work, which you might want to think about. There's also works on like IID profit inequalities. And a further direction is what like these distributions are not known to you. Like what if you only have sample access? Till now, I've been always assuming that these distributions were given to you upfront. Like, but what if I only have sample access to them and I still want to design good algorithms? Again, this is a problem which has been studied. Like there are some results known, but many open questions are still left. Good. So let me just wrap up that. Okay. So what are the main takeaways? And what's to conclude? Like the main takeaways that profit inequalities and their generalizations have many, many applications and implications, both to pricing mechanisms where they help design you simpler mechanisms, and for online algorithms where they help you go beyond the worst case analysis. They have also many, many other applications beyond these two directions, like to delegated search, two-sided markets, and like many other things. And there are many other implications which I'm sure exist, but are yet to be discovered. So I'll encourage you to think about these problems. Thank you.